Here's a few more practice problems with mole calculations. Number 7, we have 36.9 grams of gallium, and we want to know how many moles of atoms that would contain. We are switching from grams to moles. How many moles of atoms? So I start with what I have, 36.9 grams of gallium. We'll set up our proportions. To cancel the unit we have, grams, we want to switch it to moles. Anytime you see the unit mole, we're always talking 1 mole. And the mass in grams will be on your periodic table. This is the molar mass. We just have to look it up. Gallium, 69.72. 69.72. If your proportion is set up correctly, it'll tell you if you multiply or divide. If the number is on the bottom, we divide. If the number would have been on the top, I would multiply. So in this case, we take our 36.9 divided by 69.72. My original number has 3 sig figs, so I will leave 3.529. 0.529. And that would be moles of gallium. Done. Piece of cake. Now a few more that are a little more interesting. Some more fun ones. Number 8. 25.05 grams of calcium chloride contains how many chlorine atoms? Ooh, tricky. Because what we're given is a compound, and often they would ask how many calcium chloride molecules. But in this case, we're looking at chlorine atoms. Well, let's get started with what we know. We have 25.05 grams of this compound. Calcium is +2, chlorine is -1. Calcium chloride, 2 chlorine. Now this I would know how to do. I could cancel grams and change this to molecules. We're used to that. Anytime I see atoms or molecules, I'm thinking 6.02 times 10 to the 23rd. That's for a mole, which I could find the mass of a mole by using the periodic table, the molar mass. Now in this case, we have a compound, so we just have to add it up. I do not need to see work, but definitely show your formula. So we're going to take calcium, 40.08, plus 2 times chlorine, 35.45. So my compound has a mass of about 110.98 grams. Now at this point, grams and grams would cancel. I'd be at molecules. So just out of curiosity, let's see what we get. I would take this 25.05, multiply by the 6.02 times 10 to the 23rd, and divide by my 110.98. So I would get about let's go 4 sig figs. 359 times 10 to the 23rd calcium chloride molecules. We've done something similar to this. We've taken grams and switched it to molecules by using the molar mass. That 110.98 is the mass of a mole, and a mole would be 6.02 times 10 to the 23rd particles. However, that's not what this question is asking for. They want to know how many chlorine atoms would be in this sample. That's a little different. Now, sometimes people have a hard time understanding this, and sometimes it comes to them really clearly. Does this make sense? Every molecule of calcium chloride has 2 atoms of chlorine. I have a lot of calcium chloride molecules. But if I know that each has 2 atoms of chlorine, could I just take this number and multiply by 2, each molecule has 2 atoms of chlorine. If I multiply by 2, I should get the number of chlorine atoms in that sample. In other words, I'd be looking at 2.718 times 10 to the 23rd chlorine atoms. And that's what the question's really asking me for. Now again, sometimes that comes really quick and people are like, oh yeah, I get that, makes sense. Sometimes they're like, wait a second, where did you get that from? Think about it on a smaller scale. What if I had 3 molecules? If I had 3 molecules of calcium chloride, and then I asked you, how many chlorine atoms? Well, now people can actually draw it out, and you can see, oh yeah, each molecule has 2 atoms of chlorine. I have 3 molecules. This is a piece of cake. 3 times 2 is 6. There's 6 chlorine atoms in that sample. It's the same concept, but just on a way larger scale. I can't write out 1.359 times 10 to the 23rd molecules. That's crazy. It's such a huge number. But I can apply the same logic. Each molecule has 2 atoms of chlorine, so I'll multiply by 2. And that gives me the number of chlorine atoms in my giant sample. So I like that one. A little different twist. Here's another one that I really like. 9 might be one of my favorites because this is actually like lab stuff. We'll do something very similar in the lab. A student needs 64.1 grams of aluminum. How many moles? And we'd say, piece of cake. I can do this. I start with what I have. 64.1 grams of aluminum. I can cancel grams, put it in moles. Anytime I see moles, it's a 1. Anytime I see grams, it's off the periodic table. I just look up the molar mass. 26.98. The number's on the bottom, so I divide. And if I use 3 sig figs, how about 2.38 moles of aluminum? This makes sense. Every mole of aluminum is about 27 grams. I have a little more than double that. So yeah, it makes sense. I have a little more than 2 moles of aluminum. How many atoms of aluminum in my sample? Well, you have a couple options. If you already turned this into moles, you could just use your 2.38 moles of aluminum, cancel moles, switch it to atoms. And anytime I see atoms or molecules, it's the 6.02 times 10 to the 23rd. Anytime I see moles, it's a 1. Now your other option, if I wouldn't have already calculated moles, or we could go back to the 64.1 grams of aluminum, and I could set up a proportion that again would cancel grams, and I could switch it straight to atoms. There would be 6.02 times 10 to the 23rd atoms in 1 mole, and 1 mole would have the 26.98 grams, the molar mass. Do you kind of see how these would be comparable? In part A, I divided by the molar mass. This 64 divided by 26.98, that gives me the 2.38 moles, which then I would multiply by Avogadro's number, 6.02 times 10 to the 23rd, and that gives me atoms in the sample. So let's see, we plug this in, and I should get a large number, and I do. I'd be looking at either way, let's go 3 sig figs again, 1.43 times 10 to the 24th atoms of aluminum. Cool. Now here's the part I love. When we do chemical reactions, atoms and molecules react at a very specific ratio. So for this particular reaction, let's say it's a 1-to-1 ratio. For every atom of copper, I need 1 atom of aluminum. The student needs the same amount of copper atoms. Again, maybe they react at a 1-to-1 ratio of atoms, not necessarily grams. Remember balancing equations, and you have to balance the number of atoms on both sides? That's where this comes into play. What mass of copper should we measure? Okay, so again, we have a couple options. We want a sample of copper with the same amount of atoms. Well, you could use that aluminum atom. We have 1.43 times 10 to the 24th atoms of aluminum, and now I want the same amount of copper atoms. So I could say, well, I want this many atoms of copper. And so now I could do a proportion to cancel atoms and switch it to mass, which would be in grams. Anytime I see mass in grams, I go to my periodic table, 63.55 grams. Anytime I see atoms or molecules, 6.02 times 10 to the 23rd. These quantities are both for a mole, so they're comparable. We can use them on proportions. My atoms and atoms would cancel. I cannot cancel my 10 to the 23rds. My original is 10 to the 24th. So you could either just plug this in your calculator, or you could go like 14.3 times 63.55 and divide by 6.02. You could do that. And I'd be looking at, with 3 sig figs, 151 grams of copper. Now there is one more option. So you could either start with this. Here's my atoms of aluminum. I want the same amount of copper atoms. Or a shortcut. You could just start with the 2.38 moles. Moles is a unit that represents a quantity of particles. So if I have 2 samples with the same amount of moles, they have the same amount of particles. So I could say I want 2.38 moles of copper. I want to cancel moles, switch it to grams. The molar mass is 63.55 grams for every 1 mole. Moles and moles will cancel. There we go. And so it just makes it a little easier to plug in your calculator. I multiply across, and I still get 151. You get the same answer either way. It's just a little different way of looking at it. We could start with that number in moles as well. Because again, if you think about it, if I take that 1.43 times 10 to the 24th and divide by 6.02 times 10 to the 23rd, it's going to give me 2.38 moles. And then to switch moles to grams, I multiply by the molar mass. Now here's the other thing I love about this question. So check it out. We started with 64 grams of aluminum. We end up with a little more than double the amount of copper. If for this chemical reaction we need the same amount of atoms, that does not mean the same amount of grams. Copper atoms are just bigger atoms. There's more protons, neutrons. The mass is larger. Well, yeah, it kind of makes sense. Like, look at these molar masses. The molar mass of aluminum is about 27 grams. The molar mass of copper is about double. A little more than double. Well, yeah, it makes sense then that my original sample was about 64 grams. I'm going to need about double. The molar mass is just about twice as large for copper. That's good stuff. I like that. We're going to do something similar in the lab, eventually. The last little calculation in this section, number 10, this one actually isn't so bad. A diamond is often weighed in carats. 1 carat is equivalent to 200 milligrams. A pure diamond is really carbon atoms. It's a whole bunch of carbon atoms in a tetrahedral arrangement. How many carbon atoms make up a 1 carat diamond? Okay, so 1 carat would be equivalent to that. 200 milligrams. So I could start with my 200 milligrams. However, if eventually we want to know how many carbon atoms are in this sample, we're going to need to get it out of milligrams. And eventually, we're probably going to want to use the molar mass on the periodic table. But molar masses are only in grams. So you have a few options here. You could set up a proportion where you cancel milligrams and switch it to grams. 1 gram has 1,000 milligrams. Milligrams are tiny. This would cancel to put you at grams. Grams of carbon. Should put that in there. This is milligrams of carbon. Well, from there, I could cancel grams of carbon and switch it to atoms. Whenever I see grams, I know it's the molar mass on the periodic table. 12.01 for carbon. And whenever I see atoms, it's the 6.02 times 10 to the 23rd. The number of atoms in a mole, and then I have the mass of a mole of carbon. You can plug this in your calculator to get about 1.00 times 10 to the 22nd carbon atoms. There, that wasn't so bad. The only thing that threw us for a little curveball is that they gave us milligrams, which we should just make note that when you use the molar mass on the periodic table, it is in grams. So if you don't have grams, you'll need to make a conversion. Now that could either be done with a proportion, kind of like this, or if you remember your metric conversion, kilo, hecto, deca. Then comes the base, deci, centi, milli. You could also just flip the decimal spot. So in this case, I had milligrams. I wanted to switch it to regular grams. I could have just moved the decimal spot, and instead of using, whoopsie, that's kind of messy, 200 grams, there we go. I could have just gone 1, 2, 3. I could have made it 0.2 grams. And that would have saved me that first little step. Instead of dividing by 1,000, I could just flip the decimal spot. So you will need grams if by chance you were given maybe kilograms, or in this case, milligrams.